Welcome to Efiwe, excellence without stress.
Welcome guys to Efiwe, excellence without stress, and I remain your favorite chemistry tutor, Dotson. So let's get into it. Have you guys ever wondered why, for instance, that burning process tends to produce a lot of heat? Or why you feel a cool sensation as methylated spirit or petrol vaporizes from your body? Wonder no more, as this study would help you understand these things. So what study is that? Energetics and thermodynamics. Now, this particular study would be shared into different sections, which would include introduction to energetics and thermodynamics, important terms, the laws of thermodynamics, where we will discuss majorly the first and the second law. Under the first law, we'll talk about enthalpy and enthalpy change, heat of reactions, and the laws of thermochemistry, and then talk about thermodynamic equation. Then finally, we'll end it with entropy, gives free energy, and spontaneity. So what is energetics? Energetics is simply the study of energy. There's no confusing thing about it. Once you are studying energy, what you are simply doing is energetics. Then what is now the difference between energetics and thermodynamics? In thermodynamics, you are still studying energy, but you are looking at the relationship between heat energy and other forms of energy. So just take note of that. Thermodynamics is the study of heat energy in relation to other forms of energy. Now let's get into the important terms in thermodynamics. The first one is thermal energy. And what is thermal energy? Thermal energy is simply the energy that is associated with the movement of particles of a substance. Now note that I did not say it is the energy associated with movement of a substance. No, the constituent particles of a substance, once they are moving about, the energy associated with those movement of those particles, when I mean particles, I mean the atoms and the molecules, is what we refer to as thermal energy. Like if you notice, when you are boiling your sweet egusi soup and the thing begins to heat up and heat up and heat up, as the temperature increases, it will get to a point you start doing poto 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 poto. That movement of the particles is because the thermal energy has increased. So once you notice more vibration of particles, it means that there is higher thermal energy. Heat is simply the flow of that thermal energy, but we can actually use them interchangeably. We can say heat for thermal energy and thermal energy for heat, but it's more like tautological when you say the flow of heat, because the flow of heat is the flow of thermal energy. Okay, but let's go on, Now, moving ahead, temperature is now the measure of that thermal energy. It is also referred to as the measure of cold or hot of a body. And that's that basically. Moving ahead to other terms. The next important term is system. Yes, system is not your computer. System is simply anything that is under study in thermodynamics. Yeah, because in Nigeria we have this thing where we call the PC, our personal computer system. Well, let's continue. Now, the point is that once you are studying something, it is simply referred to as the system. Anything that you are studying is what we refer to as the system. So if I'm studying a reaction of ammonium chloride, let's say ammonium chloride is reacting with your sodium hydroxide. In that reaction now, you notice that ammonia is going to be produced, but let's not talk about that in this study. What I'm just trying to emphasize is the system in this case is the reaction between ammonium chloride and your sodium hydroxide, which means every other thing that I'm not studying is not a system. The reactants exactly is what I'm studying, as well as their products, because the reactants will yield their products. So the system is what you are studying, and every other thing that you're not studying is referred to as the surrounding. Moving ahead, a system can either be open or closed. It can also be isolated. And when we say an open system, it is simply a system that allows the transfer of both heat and matter, or maybe energy and matter. So if you are boiling water, or maybe yes, you are boiling water, or you're performing a reaction in an open container where the matter can live. So let's say you opened your pot and you're boiling water and the water is vaporizing, you notice that matter is transferred. And then there's also flow of energy both inside and out of the pot when you're boiling water. So in that case, that is an open system. Or maybe you're performing a reaction that one of the products is going to be a gas. Let's say you are basically thermally decomposing calcium carbonate, and in that thermal decomposition you did it in an open container. If you do that, automatically the carbon dioxide gas that will produce would leave. Hence, it is an open system, because in an open system there is both transfer of matter and energy. Now, in a closed system, on the other hand, there is only transfer of energy but no transfer of matter. Yes, so if I was performing a boiling process, and then I sealed the container such that no vapor would leave, but then I can allow the transfer of energy automatically. That's a closed system. Also, when you're performing reactions in fume cupboards, if your fume cupboard is used to produce your poisonous gas like your sulfur dioxide gas and these other gases that are very poisonous. So what happens with the fume cupboard is that it is sealed and does not allow the transfer of those gases out. So that's that basically for your closed system. Then if you consider your isolated system, it does not allow transfer of both matter and energy. So imagine your fume cupboard insulated. So if you insulate your fume cupboard so that there is no heat transfer or energy transfer, as well as there is no transfer of matter, automatically that can serve as an isolated system. Moving on, the surround. Oh, I've mentioned that the surround is simply anything you're not studying. So if I am performing a reaction of ammonium chloride and your sodium hydroxide, you notice that I performing the reaction, I'm not the person on that study. So what is happening? I am a surrounding. The beaker is not on that study. The beaker is the surrounding, the Bunsen burner or any other thing that you're supposed to use around that is not the ammonium chloride and the sodium hydroxide. Every other thing around it is the surrounding. Then we finally talk about the universe. The universe, yes, as we know, is the universe though, but it is simply a combination of the system and surrounding. So it's every other thing. The system, what you're studying and what you're not studying, every of these things constitute the universe. With that said, we'll get into the laws of thermodynamics. There are about 4 laws of thermodynamics. Zeroth, which talks about the what majorly determines our thermometer and why we have the thermometer is the zeroth law. The first, second, third law, and that's that basically. So for this particular study, we are going to be concentrating on the first and the second law. So let's get into it. What then is the first law of thermodynamics? Now, the first law of thermodynamics simply states that the total energy of the universe is constant. What this simply means is that you can't create energy, neither can energy be destroyed. It is simply converted from one form to another. So I take it again. Energy can neither be created nor destroyed, but it's converted from one form to another. So you could actually say that the first law of thermodynamics is the law of conservation of energy. Simple. To understand this energy conservation, it is important to know the different forms of energy possessed by a body. So let's get to understand them. The first thing we are going to talk about is the total internal energy. Now, the total internal energy basically consists of all forms of energy possessed by a body. Yes. So every form of energy that a body possesses is what describes its total internal energy. Now, the total internal energy of a system cannot be determined. It can't. However, a change in the internal energy can be measured. This change is as a result of heat changes and work done in the system. So anytime there is a heat change or heat transfer, or maybe work is done on or by the system, automatically there is a change in internal energy. So mathematically, it can be expressed as change in internal energy equals Q minus W. Now, mind you, U is the internal energy, Q is your heat, and W is the work done. In some cases, you can, in place of U, you can use the symbol E for your internal energy. So whichever one is comfortable for you, you can use them. So moving ahead, but in our study, we are going to be using U in this case as internal energy. So having said this, what are the important things to note about the change in internal energy? It is a state function, and it is dependent on the implication of when you say something is a state function. It simply means that that particular thing is dependent on the first and final values and independent of the pathway. One of the illustrations I like using to discuss this basically is, let's say for instance, you are asked to climb this mountain, and then there is a pathway. You go round and round and round and round and round and round. So you will notice that if somebody starts here and begins to walk round and round and round, he will cover more distance than somebody that just takes a plane or a helicopter and then drops the person right here. So you notice this. If you are asked, this is person A and this is person B, this particular person B covered more distance than the person A, but did they cover the same height? Yes. So if you are asked, for instance, person A, what height would person A cover when he gets to the top? If this is 10 kilometers, this is the person A actually covered 10 kilometers. When person B walks round and round and goes through this distance, and then you ask person B, what height did you cover? I did not say what distance, what height did you cover. You notice that it is still 10 kilometers. So it's not dependent on how you got there. Whether you suffered or you entered a helicopter, you still have the same height covered. So note, height is a state function. Why? It is simply dependent on where you started and where you are. So change in internal energy is the state function because it's dependent on the final value and the initial value. So that's that basically about state functions. Okay, so moving ahead, we'll talk about the other things that must be emphasized for your change in internal energy. Now, with that said, expansion implies a positive work done and a decrease in energy. So it's important to take note of that whenever you hear the term expansion with respect to internal energy, it means that the work done is positive. And once the work done is positive, it means that the system basically is doing the work. That positive work done by the system will cause a decrease in the internal energy of the system. On the other hand, compression implies a negative work done and an increase in energy. Heat loss is negative, and if heat loss is negative, it causes a decrease in energy. On the other hand, if heat gain is actually positive, and once you are considering a heat gain as positive, it causes an increase in the energy of the system. It actually makes sense because when you are absorbing heat from the surrounding into the system, the energy of the system is increasing. On the other hand, when you are losing heat, the energy of the system is decreasing. When you say a system does work by expansion, it means that the system is working hard and will be removing energy. So that's the whole concept behind this. Expansion implies a positive work done. Compression implies a negative work done. The positive does not mean increase. The positive simply means that the system is the one doing the work. So have this in mind, that whenever expansion is occurring in the system, like the balloon is expanding, or maybe a particular process is occurring to increase the size of something, basically that is associated with a decrease in energy if the system is the one performing the work of expansion. Then compression, basically the surrounding is now working on the system. It leads to an increase in energy, basically, but then it is a negative work done. So let's move ahead from this and get into the other things. So enthalpy is simply defined as the heat content of a body. It is mathematically expressed as the sum of internal energy and the product of volume and pressure. Yes, so you have that H, which is what we use to represent enthalpy, is the heat content. Now, did you notice that because we cannot determine internal energy, it also means that we can't determine enthalpy? That's that basically. However, a change in enthalpy can be expressed as dH equals du plus pdv. So if we want to play around that, you will notice that what we're going to have, if we have dH and we say that dH is equals du plus pdv, I hope we all know where this all came from, where we had h equals u plus pv. If you make this delta, it like opens it up and gets everything in place. Okay, so moving ahead, let's take this out. Okay, so you will now have that first of all is that change in internal energy. If you remember, change in internal energy is Q minus W, and you would also note that pdv is what we call expansion work done, and expansion work done is a positive work done. Because of this, we are going to have that dH would be equals Q minus W, which is for du, in place of du, and then in place of pdv we'll have plus W. So once this happens, you have dH as equals, so Q minus W plus W minus W plus W will have that dH is going to be equals Q. So what does this mean? It means that anytime you are asked to find enthalpy change, it simply means find the amount of heat that is gained or the amount of heat that is lost. So you could put that down as your own definition of enthalpy change. It implies that enthalpy change is simply the heat loss or heat gained during a particular process. Now, reactions can either have a positive enthalpy change or a negative enthalpy change, and this classifies chemical and physical processes into endothermic and exothermic processes. So let's see what these things are. When you say that a process is endothermic, what exactly do you mean? These are simply processes that are associated with absorption of heat from the surrounding to the system. Now you see why I had to mention the surrounding and the system initially. so that we'll be able to avoid confusion about these things. This is actually one of the places Jamb gets their confusing question. They'll be like, which one of during the endothermic process, which of these is correct? And they'll have option A, the temperature of the system increases. Option B, the temperature of the surrounding increases. Option C, the temperature of the, and so on and so forth. So just take note of this, that anytime you are referring to an endothermic process, it is simply associated with absorption of heat from the surrounding to the system. So if, for instance, I have a particular, let's say you have this setup. This is a conical flask. Our conical flask will be our surrounding now, as well as every other thing. So let's say we have NaOH and HCl. This is the system. Every other thing that is not this substance is the surrounding. So as we said, for an endothermic process, there would be movement of heat from the surrounding into the system. This is heat. From surrounding, this is the system. This is the surrounding. Every other thing outside is basically the surrounding. Now, note this, that once there is movement of heat into the system, not into the conical flask, but into the particular things we are studying, you will notice that it is referred to as an endothermic process. Now, the basic thing I would like you to take note of is when this system is collecting heat from the surrounding, hope you know that the temperature of the surrounding will start going down. So have that in mind. As an endothermic process is occurring, it is collecting heat from the system, so the surroundings temperature will now be going down, hence it will start becoming cool. However, the temperature of the system, because it is collecting that heat, would increase. So that is exactly why when you pour methylated spirit on your finger, or maybe you have a wound and you rub methylated spirit, it begins to give you a cooling sensation. Why does it give you a cooling sensation? Vaporization is an endothermic process, so it tends to collect heat from your body, and then before it vaporizes, and during that collection of heat, the process of collecting that heat reduces the temperature of your body. That's why you feel cool when you pour methylated spirit and it vaporizes. Also petrol and every other thing that does that too. So you will notice that down to the homeostatic process of your skin trying to maintain your body temperature by inducing sweating. Yes, when the water or the sweat is vaporizing from your body, what makes you to feel cool, or the reason you are sweating, is so that as the water vapor or the water is vaporizing, it tends to collect the heat from your body and reduces the temperature of your body. So have that in mind, that once it is endothermic, it collects heat from the surrounding, hence reducing the temperature of the surrounding. However, the temperature of the system is most likely going to be increased. So moving ahead, this would lead to a decrease in the temperature of the surrounding, as I stated, and an increase in the temperature of the system. Yes, the enthalpy change of an endothermic process is always positive, so have that in mind. So let's continue. So once you see a reaction and they say DH equals positive, it simply means that you are dealing with an endothermic process. Examples of endothermic processes include vaporization, photosynthesis, melting, sublimation, dissolution of sodium, potassium, and ammonium salt. So ammonium chloride dissolved in water, endothermic, sodium chloride, and all this potassium nitrate. Once you are dealing with these salts or these classes of salts, dissolving them in water is in most cases endothermic. Then you have the thermal decomposition processes. So any of these processes that you need to absorb heat for that process to occur is referred to as an endothermic process. Then we talk about the graphical representation. Now, if you are going to talk about the reason why, or the reason we have the enthalpy change as positive, is simply because the energy of the reactant is lower than the energy of the product. Anytime you are asked to find or put down a graphical representation of an endothermic reaction, just note that the energy of the reactant should be lower than that of the product. Now let's get to show that, or explain what we actually mean by that. Okay, sorry, let's take this out. So let's say you have your thermodynamic equation is represented as dH equals heat of product minus heat of reactant. We'll come across that as we go further, but I'm just mentioning it now. So which means that if the heat of change in enthalpy is going to be positive, it means that the heat of product has to be higher now, because if you have higher heat of product and lower heat of reactant, you have a positive value. But on the other hand, if your enthalpy change has a higher heat of a lower heat of product, I meant to say, and a higher heat of reactant, you have a negative enthalpy. So take note that anytime you are looking at an enthalpy change and you want it to be positive, the heat of product has to be higher than the heat of reactant. So as you can see in the graph, it's quite simple. The product is higher, reactant is lower. So once you have any graph, you want to draw a graph for endothermic, just put this one down, put the product up. Provided the product is higher than the reactant, the heat of the product is higher than the reactant, the reaction is supposed to have a positive enthalpy. A positive enthalpy is an enthalpy greater than 0. So that's that basically. Okay, so with that said, we will go to the next form of enthalpy, and that is your negative enthalpy, which is represented by the exothermic process. Now, these are basically processes associated with liberation of heat from the system to the surrounding. So it's pushing away heat from itself and pushing it into the surrounding. Let's go back to our illustrating board. So if you have a particular process, the reaction of sodium hydroxide with hydrochloric acid is actually exothermic. So just in case, don't confuse it, is exothermic. So in this case, you have that heat is going to be moving out of the system. So from here is going into the surrounding, Now as you're pushing heat into the surrounding, the implication is that the temperature of the surrounding will begin to increase. However, the temperature of the system will begin to decrease. So take note of that. As we are pushing heat out or liberating heat out from the system to the surrounding's temperature will begin. That's exactly why when you're performing a neutralization reaction, you will notice that the beaker in some cases becomes or begins to heat up. Why the beaker is heating up is because it's exothermic. It's pushing out heat from the reactant into the surrounding. And that's that basically about that. So having said that, we shall move ahead into the study. So this implies that during the process, the temperature of the surrounding would be increasing while that of the system would decrease. The enthalpy change for this process, which is exothermic, would always be negative. Now, what then are the examples of exothermic processes? Combustion processes. Yes, combustion is basically the burning of a substance in oxygen. So in most cases, your combustion reactions are exothermic. Neutralization reaction, as I mentioned, is also exothermic. Dissolution of sodium, potassium, and calcium in water is exothermic. Your dissolution of sodium hydroxide and potassium hydroxide in water, calcium hydroxide, is still exothermic. Dissolution of your acid in water, exothermic. Condensation, deposition, and freezing, all these processes are exothermic, which means that they push out heat from the system into the surrounding. Okay, so having said that, a graphical representation of an exothermic process would have that the heat of the reactant will now be higher than the heat of the product. We will discuss this particular graph majorly when we are talking about collision theory and activation energy in our study of rate of reactions. But for now, what I want you to take note of is the fact that in exothermic, the energy of the reactant has to be higher than that of the product. Remember, I gave you a particular equation. The thermodynamic equation is heat of product minus heat of reactant. So if this thing is going to be a negative value, this reactant has to be higher. That's why the product being 5 minus 7 gave us minus 2. But when you have that the product is higher, it will definitely be positive. So just when you're drawing your graph, if it's exo means that it's negative, and for it to be negative, the reactant product has to be lower. So if the product is lower, just put your reactant anywhere, then bring down your product. Make sure it is lower. This is for exo. But then for endo, heat of reactant is lower. So lower, which means just place your products above it, basically. Unless you have specific numeric values that you're supposed to position them, then you could do that. But then, generally speaking, this is what the graph represents for an exo and an endo. So that's that basically. With this said, we shall move ahead into the other parts of this study. Now, what is the next thing we need to talk about? Heat or enthalpy of reactions. Now, if you talk about the enthalpy of a reaction or enthalpy of reactions, they basically describe the enthalpy changes associated with a particular reaction that is occurring. So whenever you are looking at the enthalpy of a reaction, you are just thinking of the enthalpy change associated with that reaction occurring. There are multiple heat of reactions, and each of them have to do with the heat lost or gained. So when I say enthalpy change, I'm looking at the heat lost or gained. For 1 mole of the reaction to occur, or for one of the reactions to occur to 1 mole of a substance, or to produce 1 mole of a substance, the emphasis in heat of any reaction is just think about that process occurring to 1 mole of a substance, and that is the definition of the heat of that particular reaction. In a process where the product is the emphasis, just think about that process occurring to produce 1 mole of that substance. So basically, that heat of any reaction is that reaction occurring, the enthalpy change associated with that reaction occurring to 1 mole of a substance or to produce 1 mole of a substance. So let's discuss some of the popular examples. Starting from the first one, heat of combustion. When you say heat of combustion, combustion is the burning of a substance in oxygen, which means the heat of combustion is the enthalpy change associated with burning of 1 mole of a substance in oxygen. Remember, once you talk about combustion, it is burning of a substance in oxygen. And I told you that heat of any reaction, simply think about it, just put 1 mole. When that process is occurring to 1 mole of a substance, that is the heat of that reaction. So the enthalpy change associated with burning of 1 mole of a substance in oxygen is what we refer to as the heat of combustion. Now, it is mostly exothermic, as you can see, when carbon is combusted. So notice something about the heat of combustion. It deals with burning of 1 mole of a substance. Notice that this is not 2, this is 1. If there was 2 here, whatever value you have here will not be the heat of combustion. Once you are dealing with the heat of combustion, it must be burning of how many moles? 1 mole of a substance in oxygen. So yes, this is 1 mole of carbon. So this value here, the enthalpy change associated with burning of 1 mole of a substance, becomes the heat of combustion. This is 1 mole of hydrogen. So the enthalpy change associated with burning of 1 mole of hydrogen becomes the heat of combustion of hydrogen. Then this is 1 mole of carbon 2 oxide. So the enthalpy change associated with burning of 1 mole of carbon 2 oxide becomes the heat of combustion of carbon 2 oxide. I presume that was easy to understand though. So let's go to the next one. Heat of formation. Now, this is the enthalpy change associated with the formation. Because the emphasis here is product, we are going to be considering the products in this case. So the enthalpy change associated with the formation of 1 mole of a substance from its constituent elements. So the two emphasis here is 1 mole of a substance and its constituent elements. So any enthalpy change that you see in relation to the product or production of 1 mole of a substance from its constituent elements is what we refer to as the heat of formation. So note, the heat of formation of an element is equal to 0. That's basically because the element is already formed. So that's that. Now, if carbon and oxygen give CO2, you know these are the constituent elements of carbon 4 oxide. So which means when I produce 1 mole of CO2 from constituent elements that make up this CO2, the emphasis is 1 mole produced from constituent elements. Any heat or enthalpy change becomes the enthalpy of formation of that substance. Remember, 1 mole. If there was 2 here, whatever enthalpy change here does not describe the heat of formation. The heat of formation describes the enthalpy change associated with the formation of 1 mole of a substance. Note, from its constituent elements. Now, if I'm going to form carbon 2 oxide, carbon 2 oxide is formed from carbon and oxygen. And if it gives me 1 mole, any enthalpy change that is related to the formation of this 1 mole of a substance from the constituent element, which is carbon and oxygen, is what I refer to as the enthalpy of formation of carbon 2 oxide. Now look at this reaction. Notice that 1 mole of carbon 4 oxide was produced here. But because it was not produced from the constituent element, this enthalpy change is not the heat of formation of CO2. So have that in mind. The emphasis in the definition of heat of formation is 1 mole of a substance is produced, but then it has to be produced from its constituent element, so that any enthalpy change you notice associated with the formation of 1 mole from its constituent elements becomes the heat of formation. So that's why this one is not, because carbon 2 oxide is not a constant element, it's not an element, it's a compound. So have that in mind, that for it to be referred to as a heat of formation, constituent elements and then 1 mole of a substance. So with that said, because these are things that we need to emphasize, because when we get to solving questions and you're asked the heat of formation, it's supposed to be giving something like this, and some of you will now pick nonsense. Anyway, I hope this is clarified. Moving ahead, heat of neutralization. Now, this is the enthalpy change associated with the reaction of 1 mole of hydrogen ion or hydroxonium ion with 1 mole of hydroxide ion to form water. As we know, neutralization is a reaction between an acid and a base. And basically, in that particular reaction, the acid's most important part is the hydrogen ion, and the base's most important part is the hydroxyl ion. So which means when I'm reacting 1 mole of the hydrogen ion with 1 mole of the hydroxyl ion, it is still the same thing as reacting an acid and a base. So that particular enthalpy change associated with a reaction between 1 mole of hydrogen ion and hydroxyl ion, or 1 mole of hydroxonium ion and hydroxyl ion to give water, is referred to as the enthalpy change or heat of neutralization. Now, note, the enthalpy change is always negative for every neutralization process. The heat of neutralization for a strong acid and a strong base is always the same, irrespective of the acid or the base. If either the acid or base is weak, then the heat of neutralization decreases. Yeah, so once a strong acid is reacting with a strong base, examples of your strong acid: hydrochloric acid, sulfuric acid, nitric acid, perchloric acid, and the rest of them. Once a strong acid is reacting with a strong base, sodium hydroxide, potassium hydroxide, or calcium hydroxide, you will notice that the heat of neutralization would be the same thing. And the average value of the heat of neutralization is about 57.4, or within that range. So basically, the point about it is, once you are dealing with the heat of neutralization and you notice it is from a strong acid and a strong base, the value will be the same thing. So if HNO3 is reacting with NaOH, the heat of neutralization of this reaction is the same thing as when hydrochloric acid is reacting with potassium hydroxide, because both in these cases are strong acids and strong base. But if, for instance, one of the acid or the base is weak, the heat of neutralization would now decrease. Moving ahead. Now, if you notice the difference here now, I put the terminology standard was added. Please, whenever you now add standard, simply end your definition with under standard condition. Finish. There is no much work there. So it simply means that this is the enthalpy change associated with the conversion of 1 mole of a substance. Vaporization is liquid to gas, so you do that. It is the conversion heat enthalpy change associated with the conversion of 1 mole of a substance from liquid to gaseous state. But then, because they mention standard, you now put under standard condition. Finish. It's a very simple thing to think about. So this is the enthalpy change. That is when you are dealing with a theoretical exam. You ask, what is the standard heat of vaporization? You know that vaporization is liquid to gas. So you now say heat of vaporization is the enthalpy change associated with the conversion of 1 mole of a substance from liquid to gaseous state. Then, because they mention standard, you now put for them under standard condition. I presume this is very easy to understand. So you notice that in this case, when I'm converting 1 mole of liquid water to 1 mole of gaseous water, the enthalpy change is plus 41 kilojoules per mole. Okay, let's try out some questions to help us understand this. So they said methane, that's methane, CH4 plus 2 oxygen reacting to give water and CO2. The H is equals, that should be negative 890. The enthalpy change, that's the H in this reaction, represented by the equation above, is the enthalpy of dash. Very interesting. So what enthalpy is this? You notice that the substance is reacting with oxygen. So once a compound is burning in oxygen, it is basically a combustion process. And any enthalpy change associated with burning of 1 mole, so notice that it's just 1 mole of CH4. Because we are burning 1 mole, the enthalpy change associated with burning 1 mole inside oxygen is the heat or enthalpy of combustion. So our answer here will be B. Very simple. It's not hard. Let's try out another one. If the combustion of hydrogen is minus 285.8 kilojoules, what is the heat of formation of water? Okay, this is somehow relatively a little bit tricky. So let's consider that. It's a very simple concept, but it's a little bit tricky. So let's look at that. If the heat of combustion of hydrogen, so let's do that. When hydrogen is being combusted, it means that hydrogen is reacting with oxygen, and we know that when hydrogen reacts with oxygen, water is produced. Now, because they said heat of combustion of hydrogen, we are only going to be dealing with 1 mole of hydrogen, so which means this enthalpy change is going to be minus 28. That should be, let's confirm that. So they said is 285.8 kilojoules. Okay, so 285.8. So 285.8 kilojoules. Okay, good. Now, because we are dealing with 1 mole, when we are balancing, we'll make sure that this is still 1 mole. And to balance, we have hydrogen is balanced, oxygen is 1. So how do we make this 1 so that will not change this value? Just add half here. So in this case now, it is now balanced. So take note that when you are burning 1 mole of a substance in oxygen, any enthalpy change they give you is the enthalpy of combustion. Now, Did you notice that this enthalpy of combustion of hydrogen is still the heat of formation of water, because we are producing 1 mole of water from its constituent element. Hence, any enthalpy change associated with producing 1 mole of water from its constituent elements is also the same thing as the heat of formation of that substance. So you note, heat of formation of water is equals the heat of combustion of hydrogen. So that's that basically. So you have that basically. So you have that because the heat of formation, water is 1 mole of water is formed from its constant element. This enthalpy change is also the heat of formation of water. Hence, what is our answer going to be? Our answer is going to be minus 285.8 kilojoules. And that's that basically. So with that said, we'll try out one more question and call it off. Consider the reaction plus H plus OH minus to give water. The energy change taking place in this reaction is simply the enthalpy. As we know now, we just mentioned that is the enthalpy of neutralization. I presume that with this study, we have been able to learn some things about heat of reactions. Welcome guys to Efiwe, and I remain your favorite chemistry tutor, Godson. In this section of our study of energetics, we are going to be considering the laws of thermochemistry. But before we get into the laws, what is thermochemistry? Thermochemistry is the branch of chemistry that deals with the study of heat in relation to chemical and physical processes. So once you are considering the heat changes in relation to chemical and physical processes, that is exactly thermochemistry. It's actually a branch of thermodynamics. And then there are 2 laws of thermochemistry, which are Laplace and Lavoisier's law, and then we have Hess law of constant heat summation. Let's look into those laws. So what does Laplace and Lavoisier's law state? It states that the energy change accompanying a thermodynamic process is equal and opposite once the reaction is reversed. What does that actually mean? So we're going to be considering a particular reaction. And in this reaction, let's say for instance, you have we discussed hydrogen. Let's say is combusted to give, let's say, H2O. So the H is going to be equals negative 285.8. Now, if the forward process of this reaction has this enthalpy change, if we happen to reverse this process and make water the reactant to give hydrogen gas and oxygen gas, the same reaction but the opposite or reverse process, what this law is simply trying to say is that the value for the enthalpy change would be the same thing. However, it will have an opposite charge. So this DH will now be positive 285.8, and that's that. So you have that if a particular process is reversed, the enthalpy change will be the same thing. However, the sign will change, which means if the forward is exothermic, the backward has to be endothermic. And that's what this law is simply trying to describe. Now, going back to it, the implications of this law is 1. If the forward reaction has a positive enthalpy for a given value, the backward, positive enthalpy indicates endothermic. The backward will have a negative enthalpy for that same value, hence it will be exothermic. So if you have plus 234 as forward, it means that for backward it will be minus 234, and that's that basically. Moving ahead, the next thing that needs to be taken note of is that the amount of reactants and products are directly proportional to the enthalpy change of the reaction. Yes, which means if the amount of the product or reactant is increasing, the enthalpy change of the reaction should be increasing, and vice versa. Let's try out some questions to help us understand and buttress this point. Now, how much heat will be liberated if 8 grams of hydrogen burns in excess oxygen according to the following equation? Now, if you look at this reaction, an equation was given and the enthalpy change was given, and you are given reactants, those reactants are dependent or have a relation, a direct proportionality to the enthalpy change produced. So from this reaction, you will notice something. 2 moles of hydrogen produced minus 571.7 kilojoules of energy. Or the question says, how much heat to be liberated if we don't use 2, but we now use 8 grams? It's quite simple. So it's more like proportion. So we'll write out our equation and then get to work. So the equation of the reaction is 2 hydrogen plus oxygen reacting to give 2H2O. And we are told that the enthalpy change of the reaction is minus 571.7 kilojoule per mole. Now note, if 2 moles of hydrogen produces minus 571.7 kilojoules, the question now says 8 grams of hydrogen will now produce what heat? And that's that basically. Remember, enthalpy change is the heat given off or the heat absorbed. So what do we need to do? First of all is that we need to use stoichiometry to convert these two things to the same units. So how do we do that? Mass is equals number of moles times molar mass. So let's convert this number of moles to mass. So that's going to be, the number of moles here is 2, which is n, multiplied by the molar mass of hydrogen. Hydrogen has an atomic mass of 1. Since there are 2 atoms, it will be 1 times 2. So the mass of hydrogen, of 2 moles of hydrogen, will now be 2 times 2, and that is 4 grams. So what do we have here? Instead of writing 2 moles, what you are going to be using is 4 grams, because the units have to be the same thing before you cross multiply. So cross multiplying now, this is going to be x is equals 8 grams multiplied by 571.7 kilojoules, all divided by 4 grams. And when you do this, this is 2. And if you have that 2 multiplied by this, we are going to have 4. 1 2 times 1 is 2, 2, that's 3, 4, that should be 1143.4 or something like that. Let's check our options. Yeah, and that's that basically. So that is option C, and that's our answer, 1143.4. So if you noticed, as I said, all we needed to do was simply relation. Having in mind that 2 moles produce this heat, it means that 8 grams of this hydrogen will now produce X. And that's that. If we were given oxygen, we would use 1 mole of oxygen producing this heat. If we are given water, we'll say 2 moles of water produce this heat. But then because we are dealing with hydrogen, we had to use the number of moles of hydrogen. And why is that? Because the amount of the products or reactants basically is proportional to the enthalpy change. Okay, let's try one more question just to help us with our understanding of this concept. Okay, this one is a little tricky. So they said 0.16 gram of methane, when burnt, raises the temperature of 100 gram of water by 40 degrees Celsius. Okay, so let's take that down. I like putting down my values like when I'm solving. So they said 0.16 gram of methane. Methane is CH4. Produced a particular amount of heat which we do not know. But what that heat did is that it raised the temperature of 100 grams of water by 40 degrees Celsius. So it's important to take note of this. Methane combusted and produced a particular heat. This heat it produced is what raised the temperature of water. So let's continue. Now, with that said, the question now says, what is the combustion heat? This should be what is the heat of combustion of methane when the heat capacity, this should be specific heat capacity of water, is 4.2 joule per gram per degree Celsius. Okay, so this is going to be quite simple. The question says, what is the heat of combustion? When you are asked heat of combustion, it is the enthalpy change associated with the burning of 1 mole of a substance, and in this case it is 1 mole of CH4. So if you look at it, if 0.16 gram of methane produces this heat, what then will be the heat produced by 1 mole of methane? Because heat of combustion is simply the amount of heat produced when 1 mole of methane is combusted. That's why we have that. Once we find the enthalpy change for 1 mole, it would be our answer. So let's get to work. The first thing I think we need to do is, let's find out this heat that 0.16 produced. And how do we find it? Based on what we know, when you have your specific heat capacity, it is related to heat by H is equals mass times specific heat capacity times change in temperature. This will give us the amount of heat that this methane produced. Now the mass of water whose temperature was raised is 100 grams. The heat specific heat capacity of water is 4.2, and then you have that the change in temperature in this case is 40 degrees. Now solving that is going to be given as, that is 100 gram multiplied by 4.2 multiplied by 40, and that is supposed to give us 16,800. So the heat produced in this case is going to be equals 16,800 joules. Now why is it joules? Let's look at the units to help us understand why it is joules. Now if you look at the unit of the heat capacity, specific heat capacity, it is joule per gram per degree Celsius. So which means that this is joule, okay, I should have written that properly, but this is joule per gram per degree Celsius, which means that the value produced in this case will be in joule. So have that in mind that this is going to be joule. Now, what we have gotten from this is that 0.16 gram of methane produced what heat? It produced 16,800 joules. It was not given directly, but they told us that this heat raised the temperature of 100 grams of water by 40, and we know that heat capacity in relation to heat is expressed like this. So we can find the heat that raised this amount of water by 40 by using this formula. When you find that heat, it was produced by this particular combustion. So that's why we said 0.16 gram of methane gave 16. Therefore, 1 mole of CH4 will now be equals the heat of combustion. So why are we using this? Because heat of combustion is the heat that is produced when 1 mole of that substance is combusted. So since 0.16 gram combusted gave 168, therefore 1 mole will now give what? X. We have mole and gram, so we need to convert this so that they will be the same unit. So mass is equals number of moles times the molar mass. So the number of moles in this case is 1, multiplied by the molar mass of methane is going to be 16, as we saw in the question. But to find it, you simply do carbon is 12 plus hydrogen, which is 1, but then there are 4 of them. 1 times 4. So if you do that, that's going to be 1 times 16. Hence, the mass we are going to be using here is 16 grams. So in place of this 1 mole, you put 16 grams. Now, with this, at this point, we can cross multiply. So cross multiplying, we will have that the H of combustion will now be equals 16,800 multiplied by 16 divided by 0.16. And if you do this, the enthalpy change of combustion is going to be equals 16,800. I think this should be times. Going through this 100. So that's 16,800. Okay. Remember that the value is still in joules. Now let's look at our options. If you look at our options, our answers are in kilojoule per mole. So let's convert it to kilojoule and then check our answer. So converting it to kilojoule means dividing it by 1000. Hence, the DH of combustion of methane will now be equals 0, cancel 0, cancel 0, cancel 0, cancel 0, cancel 0. So that is going to be 1680 kilojoule per mole. Okay, so let's look at that and see if it is even in the option. And that is option E. And that's our answer basically. So when you are given a question, simply relate it as direct proportions. And once you relate it as direct proportions, you'll be able to get your answers without any hitches. Okay, the next thing we are going to talk about is Hess law of constant energy summation. Hess law is quite simple. It simply states that the enthalpy change of a particular process would always be the same, whether it occurs in one step or in multiple stepwise processes. The enthalpy change of a particular process will always be the same, whether it occurs in one step or multiple stepwise processes. Now, imagine for instance, you are given a particular job and your job is to finish, let's say you are asked to finish 4 wraps of fufu in a day. Some of us might sit down in one sitting and finish the 4 wraps, while some other people would finish the 4 wraps by eating 1. After 3 hours they eat 1. After 3 hours they eat 1. The point about it is, if you are asked how many wraps of fufu did you eat, you will notice that each person ate 4 wraps. It did not matter if the 4 wraps was done once or the 4 wraps was eaten in 4 different steps. The point is that once you are considering how many fufu was eaten in that day, each of these 2 people ate 4 wraps. Now let's describe this thing with respect to chemical reactions and not fufu. Now, if let's say let's consider a particular process. If I want to convert ice block or solid water, which is ice, to gaseous water, there are many ways to do that. I could decide to heat it directly and then sublime it. Sublime means converting it from solid to gas without intermediate liquid, and I have an enthalpy change. So let's call this enthalpy change. The value for this particular process to occur, which is the heat of sublimation of ice, is equals 66.2 kilojoules per mole. Now, the other way we can actually convert this solid to gas is we can decide first step, number 1 step, to heat this solid and melt it and this will be called fusion. So the heat of fusion of ice is the heat required to convert 1 mole of ice to 1 mole of liquid water. This enthalpy change associated with this process is about 25.2 kilojoules per mole. Then the second step is that I now have to heat this particular liquid water and then convert it. This is vaporization. Vaporization, H2O gas. The enthalpy change of vaporization of water is equals 41 kilojoules per mole. Okay, so I would like you to notice something. This particular process occurred in one step, but this one went from solid and still got to gas in 2 steps. Let's add the total enthalpy and see if it's going to be the same thing. So this let's call this enthalpy 1. Let's give them values, numerical values instead. So let's call this enthalpy 1. We know that the process is sublimation. Let's call it enthalpy 1. Yes, sorry, my pen is acting up. 1. Let's call this enthalpy 2, and let's call this enthalpy 3. So let's do this together. So when you add these two things, what did you notice? This is going to be 2.66. So that's 66.2 kilojoule per mole. So notice that it occurred in one step, it occurred in 2 steps. The enthalpy change was still the same thing. Hence, what are we getting from this? That whether a process occurs in one step or in multiple steps, the total enthalpy change would exactly be the same thing. Hence, we can now conclude that dH1 is equals dH2 plus dH3. So when a process occurs, like for instance, if I'm considering a reaction of to produce carbon 4 oxide, if carbon reacts with oxygen and directly gives carbon 4 oxide, this is going to have an enthalpy change of about, let's say, minus 393.5 kilojoules per mole. But when you are considering a different process, if carbon first reacts with oxygen and then what it gave first was carbon 2 oxide, the enthalpy change associated with this process is minus 110 kilojoules. If this particular carbon 2 oxide is then further reacted with oxygen and it combusts, the enthalpy change associated with it becomes minus 283.5 kilojoules. Notice something, when you add these two things together, you will still get minus 393.5 kilojoules. So the point is this, that if you consider a process and it occurs once, and then that same process occurs in multiple steps, the total enthalpy change of one of the steps when it occurs once is equal to the enthalpy change of the sum of the stepwise processes. And that's that about Hess law of constant heat summation. So with this said, we now move ahead into the next concept. What do we get from this? The other thing we're going to talk about before we come to applications of Hess law is thermodynamic equation. The thermodynamic equation is basically a relation of enthalpy change to the heat of reactants and products, and it's quite basic and straightforward. When you are asked to give the thermodynamic equation, it is simply enthalpy change equals heat of product plus heat of reactant. And in this case, you notice that the heat of product is equals the heat of formation of product, while heat of reactant is equals the heat of formation of reactant. If the heat of product is greater than the heat of reactants, the reaction is endothermic and positive. On the other hand, if it is heat of reactant that is greater, the reaction becomes exothermic and negative. So that's that basically. We've talked about this briefly in the earlier study. So what we're going to do is we're going to use this thermodynamic equation to solve some questions. So let's try out some questions. Now, the standard enthalpies of the formation of CO2, H2O, and CO in kilojoules per mole are these. Okay, I would like to write this down. So let's put that down. So they said that the enthalpies of formation, I like putting my values down as I am reading the question. It helps me understand it better. So the heat of formation of CO2 was given. Heat of formation of H2O gas was given, and the heat of formation of CO gas was given. So let's find out those values from the question. So they said heat of formation of CO2, H2O, and CO2 gas in kilojoules per mole are given as minus 394 for CO2, 242 for water, and minus 110 respectively. So that's what respectively means. Okay, so putting those values down. So we have minus 394 is in kilojoule per mole. Here we have minus 242, and then here we have minus 110. So these are the heat of formation of these substances. So moving ahead, back to the question. The question now says, what is the standard enthalpy change for the reaction CO plus H2O reacting to give CO2 plus H2? Okay, so what this is going to give us is we have a reaction between carbon monoxide plus H2O gas, and then when this reaction occurs, it gives carbon dioxide plus hydrogen gas. We are now asked to find the enthalpy change of this reaction. Now remember, enthalpy change is equals heat of product minus heat of reactant. So we're going to add all these products and then minus it from the heat of all these reactants, and we'll get our answer. Now it's important that you note something. Heat of formation of elements is equals 0. So let's get to work. So we're asked to find the enthalpy change. So enthalpy change of this whole reaction is going to heat of product. The products are CO2 and hydrogen. So that's going to be the heat of formation of CO2 is, that's H of CO2 plus H of hydrogen minus the heat of formation of the products, which is H of CO plus H of water. So let's add those values. So we have that the H would now be equals heat of formation of CO2 is given as minus 394. Please put your values. They are all in kilojoules per mole. Then plus heat of formation of hydrogen. Hydrogen is an element, and the heat of formation of an element is 0. So that's going to be plus 0. Minus the heat of formation of CO is minus 110. Now note, how many COs do I have? I just have 1, so times 1. This also applies in this case. This should be times 1. If there were 2, I should actually do 2CO, which means times 2. But in this case, you notice that is 1. So plus the heat of formation of water is minus 242. And how many water molecules do I have? Moles do I have? Just 1. So times 1. So with this said, we are going to have delta H is going to be equals minus 394 plus 0 is minus 394 minus 110 times 1 is minus 110, then plus minus 242. So this is going to give us bracket minus that should be 352, because this is 110, this is minus 242 minus 110 plus this is going to give us this. Okay, so if you have that, our answer is going to be minus 394 minus times minus is going to be plus 352, and when you do this, you are going to have minus 42. Remember, it's in kilojoule per mole as your answer. So that's that basically. So it's quite simple, right? So you notice that all you need to do is make sure your values with their signs are imputed into the formula accurately, and once you do that, you would have no issue solving this particular question. Okay, so let's check if our answer is in the option. We have minus 242 here, and that's our answer. We also have plus. So notice that if you have made a mistake in your signs, you could actually get either of these values. So our answer is minus 42 kilojoules per mole. Okay, so we're going to try just one more question on this before we move ahead. So the question says, if the heat of formation of aluminium oxide and iron 3 oxide, that's iron 3 oxide, are minus 1670 kilojoules per mole and minus 822 kilojoules per mole respectively, meaning that Al2O3 has this while Fe2O3 has this. So let's take that. So solving this question, let's take this out. So we are told that the heat of formation of Al2O3 is equals minus 1670 kilojoules per mole. Just to confirm, let's look at that again. So we are told Al2O3, this first, this second. So this first, this second, meaning that this will be for Al2 and this would be for minus 822. Okay, so we have that. So, and then the heat of formation of Fe2O3 is equals minus 822 kilojoule per mole. Okay, so they gave us a reaction. So they now said, respectively, the enthalpy change of this particular reaction is dash. So we're asked to find the enthalpy change for this reaction. So let's do that quickly. So the reaction is let's see the reaction again. We have Fe2O3 plus 2Al Fe2O3 plus 2Al. So that's Fe2O3 plus 2Al would react to give Al2O3 plus 2Fe. Okay, so that basically is a displacement reaction. Now, with that said, make sure it's balanced before you start your reaction. Yes, it's balanced. So we're asked to find the enthalpy of this reaction. Enthalpy change, as we know, is heat of formation of product minus heat of formation of reactant. So which means the enthalpy change for this reaction would be heat of product. The products here are heat of products, that's heat of Al2O3 times 1 plus heat of Fe, and there are 2 of them, times 2. Okay, that's the product. We are done with the product, minus the heat of reactants include heat of Fe2O3, there's just 1 of them, so times 1, plus heat of formation of aluminium, and there are 2 of them, times 2. So let's get to work. So it means that the enthalpy change for this reaction is the heat of formation of Al2O3 according to the question is minus 167. So let's put that minus 1670, and we're multiplying it by 1, plus the heat of formation of any element. This is an element. This is an element, so it's 0 multiplied by 2. Then minus the heat of formation of Fe3 is going to be minus 822, and then we're multiplying that by 1 because there is just 1 of them here, and then we are adding it to the heat of formation of aluminium, which is 0 multiplied by 2. So when you do that, you have that your enthalpy change would now be giving us minus 1670 minus bracket minus 822. That's supposed to be in kilojoules per mole. We'll get that finally. So this is going to be minus 1670 plus 822 kilojoules per mole. That's collectively kilojoules per mole. And what's our answer going to be? Minus 848 kilojoules per mole. So let's check if it's even in our option basically before we solve. So if you check and look at your option, you notice that in our option we have minus 848, and that is exactly what we got here. So with that said, we would move into the next concept to round off this study. The next thing we are going to talk about briefly is dissociation energy and bond energy. Dissociation energy is the energy required to break a particular covalent bond. So when you are looking at a covalent bond, the energy required to break that bond is the dissociation energy. If similar or a similar type of bond occurs multiple times in a molecule, the dissociation energy for each bond will differ. This is because as the similar bonds are broken, more energy is stored in the molecule, hence holding the ones left unbroken with a stronger force. So instead of dealing with dissociation energy, which varies, an average dissociation energy for similar bonds across a molecule is considered instead. This average dissociation energy is known as bond energy. Okay, so let me just briefly highlight what we mean by this. If, for instance, we consider a particular situation where I have carbon attached to hydrogen, because I know that this is a covalent bond, automatically any energy required to break it is called dissociation energy. Now imagine you had this same carbon to hydrogen occurring here, and let's say for instance it takes 5 to break this, 5 to break this, 5 to break this, 5 to break this. The total energy that would be taken in this system would be about 20. Now if I break this bond and separate this particular hydrogen, remember that this 5 will still be retained. Hence, I'll have that this particular carbon will now share 20 amongst 3. Instead of sharing 20 amongst 4 to get 555, I'll now be sharing the 20 energy. Remember, 20 is here, and then it's shared amongst 5. Now that this 20 is going to be shared amongst 3, if we share that, we're going to get like 6 point something, 6 point something, 6 point something. This is the same bond. When the first one left, it left with 5. But now that you are breaking it again, you will need to use 6 points. Why is this happening? That's 6.67, 6.67. It's simply because dissociation energy, once there are multiple of the same bonds and you are breaking, the energy retained by the system would increase, and it will be spread amongst the lower number of bonds that are there. Okay, now let's say I break this with 6.6. You will notice that the energy 20 will now be shared between 2 hydrogens, and in this case it will now be 10-10. So notice that if I break this one this whole 20 will now be shared here. So notice something, that even though it is the same type of bond, once multiple of the same type of bond occurs in a particular molecule, the dissociation energy for breaking them will not be the same thing. So instead of considering dissociation energy, we would preferably consider an average of all those energy, and that average is what we refer to as bond energy. So have that in mind. Bond energy is basically the average dissociation energy required to break a covalent bond. And with that expressed, or with that said, we will move on. Now, analogous to bond energy is what we refer to as lattice energy. So lattice energy is simply the enthalpy change associated with the formation of ionic bond from gaseous ions, or breaking of ionic bond to give gaseous ions. What do we actually mean by this? So consider a particular process. It's just like the bond energy for ionic compounds is lattice energy. So if I have, for instance, sodium chloride, solid, and I need to dissolve sodium chloride to get to an aqueous solution of sodium plus an aqueous solution of chlorine ion. So this step can occur once, and you have that this is what we refer to as the heat of dissolution. So the heat of dissolution in this case is given like this. Now, having said this, for this particular process to occur, the very first thing that happens is that sodium chloride is broken down into its gaseous ions. First of all, it is broken down into its gaseous ions. So sodium chloride is broken into sodium gaseous ion and chlorine gaseous ions. And the energy required to break down a particular ionic bond to form the gaseous ions, or to bind them together, is what we refer to as lattice energy. In most cases, lattice energy is represented by capital U. So you have that. This is the lattice energy. Lattice energy. So anytime you are talking about lattice energy, you are looking at the energy required to break an ionic bond, or energy required to form an ionic bond. When an ionic bond is being broken, take note, it involves a positive lattice energy. But when an ionic bond is being formed, it involves a negative lattice energy. So in this case, where we are breaking the bond, it is going to involve a positive lattice energy. Now, after this occurs, for us to get to an aqueous solution, water has to be added or attached to these particular gaseous ions to make them aqueous. And the addition of this water is what we know as hydration. Now, the heat of hydration is going to be a negative enthalpy change. Why is it negative? Because bond formation is usually associated with exothermic processes, while bond breaking is associated with endothermic processes. So in this case, it will be negative. So having said this, according to Hess law, you will notice that this particular heat of solution is going to be equals your lattice energy, which is always positive, plus your negative value of heat of hydration. So with that said, the implication is that whenever you are dealing with heat of solution is going to be lattice energy plus heat of hydration. But we already know that heat of hydration would always be negative. So once you introduce that, you have your value as this. Now, this is Hess law applied, but this particular cycle that is associated with ionic processes. When you apply Hess laws to ionic processes, this cycle is what we refer to as Born-Haber cycle. So two German scientists came up with this particular cycle, and this cycle is what we refer to as Born-Haber cycle. So talking about the Born-Haber cycle, this is basically Hess laws applied to an ionic process. So take dissolution of ionic compounds, for instance, in water. It requires the breaking of the ionic bond to form gaseous ion, which involves lattice energy and hydration of ion. So when you show this in a cyclic form, what you are trying to represent, or what you are showing, is what we refer to as the Born-Haber cycle. So I'm just mentioning this just in case. So let's consider this question. A chemical reaction in which the hydration energy is greater than the lattice energy is referred to as dash. Okay, quite simple. Now, for us to understand this, we will need to go back to our screen. Remember that we said that if you are considering heat of dissolution, the heat of dissolution or heat of solution is equals lattice energy plus heat of hydration. Notice that I said that lattice energy for a dissolution process is always positive, while heat of hydration for a process is always negative. So with that said, if we are now looking for a condition where heat of hydration is higher, let's create that solution. So we are going to give values, a lower value to our lattice energy, so +5, while we give a higher value to our hydration energy or heat of hydration. So higher value, anything above 5, but we'll notice that it is always negative, so -7. So which means that if we are looking for the heat of solution, it is going to be +5 plus bracket -7. So what is going to happen here? The enthalpy change of heat of solution will now be -2. Notice this, because it is -2, it means that this process is exothermic. Why? It has a negative enthalpy change for the solution. Now, notice if the hydration energy is greater, it will be negative, because the hydration energy is always negative. So if it has a greater value, this whole heat of solution will be negative. Having said that, if you look at this, our answer where hydration energy is greater than lattice energy, this reaction is going to be referred to as an exothermic reaction. With this, we've come to the end of this part of the study. Do join us in the next part. Hi guys, this is Efiwe, Excellence Without Stress. And in this section of the study, we are going to be considering second law of thermodynamics and spontaneity. For you to be able to understand or grasp fully the second law of thermodynamics, it's important we understand the term spontaneity. Spontaneity is simply a property of being spontaneous. And when you say something is spontaneous, it means that it does not require external factors for that particular process to occur. Let's consider this particular process, for instance. So imagine you have a ball sliding down into a valley. So this is my valley, and then you have this. Okay, no, my valley is looking somehow. Okay, so yes, let's work with this anyway. And this is a ball. Now, if I call this ball A and I have ball B, you will notice that the movement of ball A into the valley is going to be spontaneous, and the movement of ball B out of the valley would require an external force. And what is that simply trying to say? A spontaneous reaction, a spontaneous process does not require any external force. Just like when this ball is rolling in, it just rolls in basically without any external force acting on it. But in the case of ball B, it would need a push for it to be able to come out of this valley. So that's basically what spontaneity implies. A spontaneous reaction is basically a reaction that does not require external force. Now, there are two major factors that affect processes of spontaneity, or could make a process spontaneous or non-spontaneous. And the two major factors are change in entropy of the universe, and then you have your change in Gibbs free energy. So let's get to understand entropy before we get to understand the entropy of the universe. This is the degree of disorderliness of a body. So anytime you are describing entropy, it is simply a measure of disorderliness of a body. Then you talk about the change in entropy. The change in entropy is simply a measure of the system's thermal energy per unit temperature, which is unavailable for doing work. Mind you, change in entropy is a state function. Now, I have described what state function is in earlier videos, but let me just say it again, that state functions are simply dependent on initial values and final values. Okay, with that said, we go to the next thing. Now, having described entropy and change in entropy, it is also important that you have this in mind, that an increase in disorderliness of a system would denote an increase in entropy, hence a positive entropy change. So anytime you notice a process and that process leads to an increase in disorderliness, the implication is that it is leading to an increase in entropy, and the entropy change will be positive. Examples of such processes include vaporization. Yes, conversion of your liquid to gas. Liquids are more organized, gases are less organized. Hence, converting a liquid to a gas will mean that you are increasing its disorderliness. Hence, positive entropy change. Decomposition is basically a process of breaking down something. When you break it down, you notice that it is no longer together but now in separate parts, hence increasing entropy. When you dissolve a substance in a solution, in a solvent, I meant to say, you will notice that the constituent particles of those substances would spread into more simpler or smaller forms, and those smaller forms are easily dispersed, increasing the disorderliness, hence a positive entropy change. If you combine two gases, particular mole of gas and another mole of gas, that also denotes an increase in entropy. Now, any reaction that tends to increase the amount of gases in a system basically describes an increased entropy. So if you have a particular reaction, for instance, let's consider the Haber process, where you have nitrogen combining with hydrogen, and then this is going to give ammonia. All these things are gases, so you have gas here, gas here, gas here. So if you notice on this side, you have, balancing it though, this is going to be a total of 1 plus 3 moles, which is 4 moles of gases, while here you have 2 moles of gases. So if you are asked, on which of these sides will you have a higher entropy, the side with a higher entropy is the side with more number of moles of gases. So any process that will lead to the formation of more gases is indicating a positive entropy change. So if I reverse this process and then have N2 plus 3H2, this is a gas, this is a gas, and this also is a gas, balancing 2. If you have this process now, you will notice that breaking down ammonia to form nitrogen and hydrogen would have a positive entropy change. Basically that's that. Okay, having said that, we move ahead to the next concept. Now, the other example of something that would lead to a positive entropy change is melting and sublimation. Anything that has to do with breaking down into simpler forms increases disorderliness, hence increasing the entropy. On the other hand, a decrease in entropy is basically caused when there is a decrease in disorderliness, and that indicates a negative entropy change. Examples of such processes simply include freezing, condensation, deposition, or any other process that reduces the amount of gases. These things basically are what leads to your negative entropy. So if you have a condition or a situation, take for instance, let's say you have a reaction, thermal combustion of hydrogen, for instance. So if hydrogen is combusted to give liquid water, H2O, liquid, you have balancing out, you have 2 here and 2 here. Notice something, the gases on this side are 3 moles of gases, and then on this side you have no gas, so 0 mole of gases. What are you indicating? You are reducing the number of moles of gases, hence you are reducing the entropy. And if you are reducing the entropy change is going to be a negative entropy change. So mind you, any process that reduces the number of moles of gases indicates a negative entropy, but if it increases the number of moles of gases, it indicates a positive entropy. Okay, with that said, we move ahead. Now, before I get into the change in entropy of the universe basically describes a combination of the system and the surrounding, and we already know that the system is what you are studying while the surrounding is what you are not studying. So when we say change in entropy of the universe, we are looking at a sum of the change in entropy of the system and the entropy change of the surrounding. So putting those two together would give us our entropy of the universe. So if we are to illustrate that or represent that, we would have that the entropy of the universe, which is the S of universe, would be equals the S of system plus the S of, sorry, this should be, let's write this properly. Okay, so you have the S of your system plus the S of surrounding, and that is basically going to give you the entropy of the universe. Now, how does the entropy of the universe affect spontaneity? The second law of thermodynamics states that for a reaction to be spontaneous, the entropy change of the universe should be positive. And what this simply means is that there should be an increase in the entropy of the universe. Now, how are we going to get a positive entropy for the universe? First of all, you will get a positive entropy for the universe if both your entropy of system and entropy of surrounding are positive. So entropy of universe would be equals positive. First condition, you could put that down. Entropy of universe equals positive if both entropy of system and surrounding increases. So in the case where, or you could say, or entropy of universe would be positive if both enthalpy changes, ds, of system and surrounding are positive. So just have that in mind, that once the system entropy change is positive and that of the surrounding is positive, it means that you have a positive entropy change for the universe. Now remember, according to the second law of thermodynamics states that once the entropy of the universe is positive, the entropy change of the universe is positive, it means that the reaction would be spontaneous. So any process that will lead to a positive entropy of the universe would automatically imply that you would have a positive entropy. So reactions like explosions, when you have explosions of, maybe for instance, you have dissolution of let's say sodium inside water, and it tends to, as I said, dissolution leads to a positive entropy for the system. The sodium inside water is the system, so when it dissolves, it becomes the change in entropy becomes positive, and as a result of that, if it leads to an explosion, it tends to affect the environment by increasing the disorderliness in the environment. So you notice that when you are looking at processes that leads to explosion, the implication is that those reactions are supposed to be spontaneous, because both the change in entropy of the system and that of the surrounding are both positive. Okay, having said this, the second condition that we are going to consider to have a positive entropy of universe, for us to have a positive entropy of universe, the second condition is if you have a negative entropy change for your system, then it means that the negative entropy change for the surrounding must be greater for the entropy of the universe to be positive. So in a situation where you have that, let's say for instance, entropy of uni, you have a negative value for entropy of your system, and you have a positive value for the entropy of your surrounding. If this is if this is -2, if you are going to have a positive value for the entropy of the universe, it means that the change in entropy of the system and of the surrounding has to be way greater than -2. So if it is +3, it's still going to be a positive one. So just have that in mind, that when you have a negative entropy for the system, it means that the change in entropy for the surrounding must be greater if you are going to have a positive entropy for the universe. Now remember, the reason we want to have a positive entropy change for the universe is because if you have a positive entropy change for the universe, the reaction becomes spontaneous. Now, if you have negative entropy change for both your surrounding and your system, that reaction will never be spontaneous. So any process that reduces the disorderliness in both the surrounding and the system will never be spontaneous. Okay, so with that said, let's move ahead. Having said that, now we have understood the second law of thermodynamics, and it states that for a reaction to be spontaneous, the entropy change of the universe should be positive. Now, the truth is that stating this law like this is more or less abstract. How do I mean, or what do I mean? If you are asked to find the entropy of the universe, it is more or less far-fetched. The reason I'm saying this is because the universe consists of the surrounding and the system. Now, surrounding is everything that you are not studying, which means that if you are going to properly calculate the entropy of the universe, you need to consider the environment you are in. And in most cases, it is hard to get the entropy of your entire environment. Hence, instead of using the entropy change of the universe to determine spontaneity, Gibbs free energy is preferably used. So, another thermodynamic property used to determine spontaneity of reaction is free Gibbs energy. And this is used because determining the entropy change of the universe is far-fetched and abstract. Gibbs free energy is simply the amount of usable energy readily available for work in a system. Now, this change in Gibbs free energy is what we refer to as a state function. Why is it a state function? Because as you can see, Gibbs free energy is dependent on the final and the initial values only. So have that in mind, that instead of using the change in entropy of the universe, Gibbs free energy is preferably used because we can actually get the values for Gibbs free energy. Now, looking at Gibbs free energy, the change in Gibbs free energy is expressed as dg equals dh minus t ds, and the implication is we can actually find these values. Once you have dg, you simply do dh minus t ds and you have your value. Now dg, as we know, is change in Gibbs free energy. dH is change in enthalpy. T is absolute temperature. Or you could say temperature in Kelvin, which means if you have your temperature in degrees Celsius, you should convert to Kelvin before you solve. And then finally, your ds is change in entropy. So that is that. Once you have these values, you will be able to determine your Gibbs free energy without any hitches. Okay, having said that, for a reaction to be spontaneous, the change in Gibbs free energy is supposed to be negative. In some cases, you see it represented as less than 0. So always have that in mind, that for a reaction to be spontaneous, change in Gibbs free energy must be negative. This type of reaction is also referred to as an hexagonic process. So once you are looking at a reaction and you notice that that reaction has a negative change in Gibbs free energy, the implication is that it is going to be spontaneous, yes, and is also referred to as an hexagonic process. So if we want to restate the second law of thermodynamics, we can say that for a reaction to be spontaneous, the change in Gibbs free energy must be negative. So we'll now be considering those different scenarios where you have a negative and a change in Gibbs free energy. But before that, we have that if the G is positive or greater than 0, the reaction is not spontaneous, and such processes are referred to as endagonic processes. So your hexagonic processes have negative change in G and they are spontaneous, while your endagonic processes have positive change in G and they are not spontaneous. Finally, if your change in Gibbs free energy is equal to 0, the reaction is a reversible process that is in equilibrium. So mind you that once the G is equal to 0, it is a system in equilibrium. Okay, having said that, we are going to be going to the analysis to find out different scenarios where the G can actually be spontaneous or not. Now, if you have a condition or a scenario where you have change in enthalpy as less than 0, that is negative. When you have a negative enthalpy change, it means that heat is liberated, so it's exothermic. So if you have a change in enthalpy as less than 0 or negative, and your change in entropy as positive, it is spontaneous at all temperatures. The reason is because dG would always be less than 0. So let's prove that. So going to our screen. So on our board, they said if you have dH as negative and ds as positive, dG will always be negative. Let's prove that. So you have that dG is equals delta H, change in H, minus the TDS. Now, if we have a negative value here, and we find out that this minus sign multiplying through would eventually still be a minus sign, the only way this is going to happen is if this ds is positive, because when minus times the positive, it still remains minus. Please, minus and minus coming together, you would still have a negative value. So that is why we said once you have a negative enthalpy and your ds is positive, this minus will multiply through and keep this product as minus. Hence, the negative here plus the negative here would always give us a negative sign. Okay, so we're going to consider the next scenario. And what is the next scenario? If we have a positive enthalpy, that is an enthalpy change greater than 0, or where it's an endothermic process, a positive enthalpy indicates that the enthalpy change is greater than 0, so it's plus value, and you have a positive entropy. The spontaneous reactions only occur at high temperature where TDS is very large. Now, when it is spontaneous, it means that dG is less than 0. So let's do our analysis. So at what temperature are we going to have a negative change in Gibbs free energy for this reaction to be spontaneous? So if dH is positive and you have that ds is positive too, dG would be negative when? Let's find out. So you have that if you have dG and it is equals dH minus TDS, if you have a positive value here, which is what we are indicating, and then you have a negative value, and you have T multiplied by a positive S. Now, if this negative is to open this, it will remain negative. And for these two to combine and be negative, it means that this particular product must be greater than this particular value of DH. For this product to be greater than the value of DH, it means that T has to be very large. So which means if T is very large or high, if T is very high, it keeps TDS negative. Hence, when it combines with a positive DH, which is lower, the implication is that you will still have a negative value. So let's try out something. Imagine, for instance, I tell you that the enthalpy change is plus 400, and then I have minus, I have a given temperature of 300 Kelvin, and then a positive value here of plus 30 joule per Kelvin. Now, if you happen to do this, your change in Gibbs free energy would now be given as 400 minus this. If you multiply this through, this is going to be minus 9,000. So notice, because you have a very large TDS, this value is still going to be negative, and this is going to be minus 8,600 joules basically. So you have that basically, that the change in Gibbs free energy is still negative. What enabled this particular change in Gibbs free energy to be negative is because we had a high temperature, or a temperature that is high enough to counteract the positive enthalpy change. So remember, we want to always have a negative value. For us to have a negative value, when the enthalpy change is positive and the entropy change is positive, it means that the temperature has to be very high. So that's that basically for this. So we go to the next scenario. Now, the next scenario we are going to be considering is when you have a negative enthalpy change and a negative entropy change. Remember, for a negative enthalpy change and positive entropy change, any temperature at all is still going to be spontaneous. For a positive entropy change and a positive enthalpy change and a positive entropy change, it is only spontaneous at a high temperature. But when you have a negative enthalpy change and a negative entropy change, it is supposed to be spontaneous at low temperatures. And the implication is that TDS is supposed to be small. Let's find out why. So, to find out why is quite simple. So we have that our DG, okay, let's outline. DH is supposed to be negative, and then if your DS is also negative, DG will now be negative when would DG be negative? Because why we are looking for conditions where DG is negative is because if DG is negative, it will be spontaneous. If DG is not negative, it will not be spontaneous. So let's do that together. So that's going to give us DG equals DH minus TDS. So if we have DH here as a negative value, and this becomes minus bracket plus minus DS, what is going to happen here is that we'll have negative, this minus opens up this bracket, and this minus times minus will turn this into a plus. So plus TDS. Now, because DH is possessing the negative value, it means that this DH has to be greater than the product of TDS for this to remain negative. And for us to be able to do that, we'll have to use a low temperature. That low temperature will now affect this particular entropy change and reduce it such that this is greater. And when we now do the difference, automatically it would have the sign of the bigger number, which is going to be the enthalpy change. So mind you, now when we do this, take for instance, we had minus 400 here, and then we have minus the temperature. Let's say the temperature is 0.5, and then maybe we have a negative 400 entropy change. Now, for us to maintain a negative temperature or a negative enthalpy, Gibbs free energy change, this temperature has to be relatively very low. You get, because if it is high, automatically is that it's going to affect this and change this. So let's say we have minus 400. Then opening up, we'll now have minus. This times this is 200. 200 minus 200 times this will become plus 200. Now, because we have a very low Kelvin temperature, this is now still going to give us minus 200. Give us minus 200 joules. So the point about it is this, that once you have a negative enthalpy and a negative entropy, to maintain a negative G, we would need to have low temperature. So the temperature has to be very low for us to maintain a negative G. Why? If you have a negative and a negative, the negative here would affect this and turn this to positive, meaning that the enthalpy change has to be greater than the product of TDS. And to get this product of TDS low, we'll need to use a low temperature. Finally, we'll consider the last one, which is a condition where you have a positive enthalpy and a negative entropy. For this particular one, it's not spontaneous at any temperature. dg would always be positive. We can actually show that dg would always be positive at any point. Once you have a positive enthalpy, if the H is positive and the S is negative, it is always going to be positive. Why? If you have dg and this is equals positive value, okay, the H, let's do this, TDS. So if you have dg and this is positive, minus bracket T minus ds, you will notice that this minus will open the bracket, so you have positive minus times this will become plus TDS. So this is positive value of H, and this is positive. Because of this negative value of S, the minus opens this up and turns this minus into plus. So you have plus and plus, which means dg would always be positive. So even if you want to use a high temperature or low temperature, dg will always be positive. So note, a reaction where the enthalpy is positive and entropy is negative cannot be spontaneous. Cannot be spontaneous. So with that said, I presume we've understood some things about it, and before we end this study, we are just going to look through just one question to solve on entropy in relation to Gibbs-free energy change and enthalpy change. The reaction represented by the equation C plus H2O plus gives CO plus H2 was carried out at 27 degrees Celsius. If the enthalpy change was 4,500 joules, so I would like to write down my values so that we'll get to solve. So we are told that it was carried out at a temperature of 27 degrees Celsius. But remember, we do not use degrees Celsius. We have to convert it to Kelvin by adding 273, and that is going to give us 300 Kelvin. Okay, then we are told that the change in enthalpy was 4,500 joules. Okay, with that said, we're also told that the entropy change is plus 12 joules. So let's put that down. Entropy change, ds, is plus 12 joules. And then we were asked to find, what were we asked to find in this question? What was the free Gibbs energy of this particular reaction? Now, they were even good enough to give us the formula. So let's find this. So dg is going to be equals dh minus tds. So which means if you are looking for Gibbs-free energy here, dh in this case is 4,500 minus the temperature is 300 Kelvin multiplied by 12. If you do this, we are going to have dg equals 4,500 minus 3,600. And when we do that, we are going to have that our final answer would be equals plus 900. So what are you noticing from here? Since dg is positive, this reaction is not spontaneous. The implication is that it is going to require an external force, an external catalyst, or external things to make this reaction to start. It needs to be ignited by something. Let's see if our answer is in the option, and you have that our answer is option D. With this, I presume that you have learned a lot about energetics. Thank you very much for joining us, and make sure you answer and solve the questions in the app.